Welcome students. So till now we have seen the method of substitution for definite integrals and several properties of definite integrals. By using these properties we can solve very complicated problem of definite integrals in a much simpler way. So let us try some more examples and explore how we can solve complicated problems in a much simpler way. Now let us take examples. Example 1. So if I ask you to compute this integral and you start integrating it by different techniques, you may be in trouble, but if you use properties of definite integral then it becomes very simple. So you may try to think in this way, that since you have limits from -2 to 2, so if you have an integral of this kind and you know that if the function is even, then this becomes 0 to twice of 0 to a fx dx for even function, and this becomes 0 for odd function. So we must first try to find out whether this integrand is odd or even. So if fx is this integrand, so let us check it whether it is odd or even. So we get here we will get plus sign because it is even power and cos of minus x is cos x. Therefore we are getting that f of minus x is minus fx. So integrand is odd function, hence value of the integral, say it is I, will be 0. You can see that by using the properties of definite integrals you can very easily integrate and find out the value to be 0 of a very complicated problem. Let us take another example. One approach to solve this problem is you can try to rationalize it by multiplying the corresponding conjugate, say root x minus under root 1 minus x, and then try to solve it. But I will not be using that approach. I will try to see whether we can use properties of definite integral. So say this is I, so by using the property that if 0 to a fx dx is same as 0 to a f a minus x dx, so I is equal to 0 to a 0 to 1 root x, sorry, root 1 minus x root 1 minus x and root 1 minus x dx, that is 0 to 1 under root 1 minus x under root 1 minus x plus under root x dx. So if say this is 1 and this is 2, if we add these two equations we get on the left hand side we get 2i, and on the right we get dx. So you can see the numerator and denominator is same, hence get cancelled and hence gets cancelled. So we get 1 and hence I is 1 by 2. So, you can see that it seems that the problem is very complicated, but you can very easily solve it by using the properties of definite integrals. Let us take another problem. Example. So, one simple approach to solve this problem, you replace sin square x by 1 minus cos 2x by 2. I am not going to use this approach. Instead, I will be using property of definite integrals. So, let us see whether this function is even or odd. So, sin square of minus x is sin square x, therefore, this function is even, hence you can write this integral as 0 to pi by 2 twice of 0 to pi by 2 sin square x dx. Now, let us use another property which says that 0 to a fx dx is same as 0 to a f a minus x dx. So, you can write this by using this as 0 to pi by 2 sin square pi by 2 minus x dx. This will give you twice of 0 to pi by 2 sin pi by 2 minus x is cos x. So, you get cos square x dx. Now, if you this is I, so say this is 1 and this is 2. So, again by adding 1 and 2 you get 2I is equal to twice of 0 to pi by 2 sin square x plus cos square x dx, which is 1, we know that. So, we get 2 into pi by 2. So, value of the integral is therefore, so we got 2I equals to pi. So, value of the integral is therefore pi by 2. So, you can see that another a very beautiful use of two properties of definite integrals which can be used to solve a very complicated problem. Let us take another example and see how simple the integrations are if you are able to use the formula for definite integrals correctly. At the very first instance, it seems a very complicated problem as usual, but again by using the property that 0 to a fx dx is same as zero to a f a minus x dx, we can write that I will be equal to say this is equation 1, 4 plus 3 sin pi by 2 minus x by 4 plus 3 cos pi by 2 minus x dx. So, I will be therefore equal to log of 4 plus 3 cos x by 4 plus 3 sin x dx. Now, again add 1 and 2, we get 2I on the LHS, and on the right we get log of 4 plus 3 sin x upon 4 plus 3 cos x plus log of 4 plus 3 cos x by 4 plus 3 sin x dx. You know that log m plus log n is log mn. So by using that you can immediately see that you get four plus 3 sin x on 4 plus 3 cos x into 4 plus 3 cos x by 4 plus 3 sin x, which gets cancelled. So you get 2I equals to 0 to pi by 2 log of 1 dx. So 2I is therefore 0, hence I is 0. I hope you must be learning how to use these beautiful formulas of definite integrals and evaluate complicated integrals. Let us take one more example. This is our final example, then we will be moving ahead towards application of definite integrals in finding out area between a line and a curve. So let us take this x e to the power x so we can use integration by parts to find out this definite integral. So if we say this is our function first and this is our function second, so by part integration we get first function into integration of second. So we get x equals to 0 to x equals to 1 minus 0 to 1, differentiation of first will give you 1 and integration is e to the power x dx. So we get 1 minus 0 minus e to the power x, integration of this is e power x from 0 to 1. So we get e minus 0 minus e minus e to the power 0, which is e minus e plus 1. So answer is 1. So this is not the end, we shall take up later more complicated problems, miscellaneous exercises we will be doing, where we will be using again all these properties and solve lot of complicated definite integrals. For the time being, let us start application of definite integrals. In our very first lecture we have discussed several problems where we have discussed several cases: area bounded between a line and a curve, area bounded between two curves, area bounded between three curves, and so on. So we shall take all these cases one by one from here onwards. Let us take area under simple curves. Case 1. So assume that this is your y axis, this is x axis, and this is some function f x which is always positive. This is the line x equals to a and this is the line x equals to b. This is the line y equals to 0, and this curve you know that it is y equals to f x. So how to find out the area? So what we have done, you know that we divided it into several very thin rectangles, right. So we can take the width of say one rectangle as dx in this case, and height of this rectangle will be y, height of this rectangle will be y. So the area of elementary strip or rectangle is y into dx, y is the height and dx is the width. Now if you so you have this elementary area dA, dA is elementary area. So if you integrate this dA from x equals to a to x equals to b, it gives you the required area. Let me shade it. So required area, it will give you the required area which is bounded between 4 curves fx, x equals to a, x equals to b and y equals to 0. So this will give you the required area A. So formula is a to b y dx. Now there are cases where this trick will not work. For example, if you have a curve like this where x is given in terms of y and the area is bounded between two horizontal lines, say y equals to c to y equals to d, then how will you evaluate the integral? So instead of dividing the area by vertical strips, we divide the area by horizontal strips, and we say that this width of this rectangle, elementary rectangle or elementary strip is dy, and height of this strip will be x governed by this equation. So elementary area is x dy, which is our elementary area. Now if we integrate it from y equals to c to y equals to d, we get the required area. So the formula in this case will be y equals to c to y equals to d x dy. So this was case 2. Let us see case 3, where your function is all below x axis. So this is your fx, which is all negative from a to b. This is the line x equals to a, this is the line x equals to b, and this is the required area. So again the formula by similar logic will be a to b fx dx, but since fx is negative throughout, value of a will be negative. Therefore for required area you have to take modulus of the final value. So required area will be mod of a. Now let us take another case where function is not throughout negative or not throughout positive, that means it changes its sign. Then what will happen? So let us take case 4, where you have a function, this is your y axis, this is your x axis, and you have a function which is changing its sign. Say this is a, this is b, and this point of intersection of the function fx is c with x axis. So you want to find out area of the function which is bounded between x equals to a and x equals to b and x axis. So in this case total area A you will not be able to get by directly integrating it from a to b. So you have to integrate and get, say, area A1 from a to c. Say this is A1 and this area is A2. and you get area A2 by integrating it from C to D. So total area required will be A1 will be positive because fx is negative from C to D, sorry C to B, this is C to B. Since function is throughout negative from C to B, so A2 will be negative, so total area A will be A1 plus mod of A2. Now let us use all these facts and solve some very simple problems at the beginning. Say for example, let us find out area of a circle x square plus y square equals to a square. So if this is your x axis, sorry, this is your y axis and this is your x axis, and the circle is this. So you know that the circle is symmetric about both x and y axis, so the total area of the circle is also symmetric. So if we evaluate this area, then we can multiply it by 4. So if this area is A, so total area is 4 times area of this circle which is lying in the first quadrant. So 4 into A. How to get A? So draw a vertical strip of dx length whose height is y. So A will be y dx, x goes from here to here. So the center of the circle is 0 0 and this point will be a comma 0. So x value will start from 0 and it will go to a, and y value will be computed from the equation of the circle. So you get y equals to plus minus under root a square minus x square. So for each value of x you get 2 values of y. So positive value of y will give you the upper branch of the circle which lies above x axis, and negative value will give you the lower branch. So this is equal to 4 times 0 to a square minus x square dx. Now integration of this is known to you, so you can directly put the value. This is x. So x goes from 0 to a. Now put the values of upper and lower limits. You get, so at a this will be 0 because of this term, and this term will give you 1 by 2 a square sine inverse 1 which is pi by 2 minus at 0 this is x, right. So at 0 it will be 0 because of x, so you get 0 here, and then at 0 sine inverse 0 will be 0, so you get 0. So final answer is pi a square. Now we have done this calculation by taking vertical strip. The same thing can be done by taking horizontal strip also. So let us see how to do that for the circle. So let us draw the circle again and let us see how to do it by using horizontal strip. Let us take this horizontal strip whose width is dy and length is x, governed by the equation of the circle. So, x will be in this case plus minus under root a square minus y square. Since we are using this branch, so positive value of x will be taken, negative value will be giving this branch of the circle. So, total area required, area of the circle, is equal to 4 times x dy. Now, what are the limits of y? So, this point is 0 comma 0 and this point is 0 comma a. So, y goes from 0 and it goes to a, 0 comma a. So, y goes from 0 to a and value of x will be taken positive because you are on positive side. So, for this branch 0 to a under root a square minus y square dy, again by using the same formula 1 by 2 y under root a square minus y square plus 1 by 2 a square sin inverse y by a, y goes from 0 to a. So, again at a it will be 0 and at a this will give you 1 by 2 a square pi by 2 and at 0 it will be 0 and at 0 again it will be 0. So, you get again pi a square. Let us take one more example and find out area of ellipse x square by a square plus y square by b square equals to 1, where a is greater than b. So, this ellipse will look like something like this. Again, since this ellipse is symmetric with respect to both x and y axis, so we may compute only 1/4 of the area and then multiply it by 4 to get the total area. So, total area is 4 times this area A, and this area A, if you use vertical strip, will again be given by y dx, where x will take values from here to here. So, for this ellipse, this is center 0 0, this is a comma 0, this is minus a comma 0, this is 0 comma minus b, and this is 0 comma b. So, for this region x minimum is 0 and maximum is a. So, we get 0 to a. Y value you get it from the equation of the ellipse, and to get that you need to solve it. So, you get y equals to plus minus b under root 1 minus x square by a square. So, y is plus minus b by a under root a square minus x square. So, for each value of x you are getting 2 values of y, but since you are using the portion of the ellipse which is lying above x axis this, so you will be taking positive sign. So, we get b by a under root a square minus x square dx. So, we get zero to a, which is equal to four b by a 1 by 2 x under root a square minus x square plus 1 by 2 a square sin inverse x by a. Total area is therefore 4b by a 1 by 2 x under root a square minus x square plus 1 by 2 a square sin inverse x by a. So 4b by a into, at a it will be 0 and this will give you 1 by 2 a square pi by 2 minus 0 because at 0 it is 0 and this is also 0. So we get 4b by a into a square pi by 4 pi ab. Similarly, this we have done via vertical strip. Let us do it by using horizontal strip. Horizontal strip. So let us draw the ellipse again. This time we will be taking horizontal strip whose width is dy and length is x. This point is 0 b, this point is 0 minus b, this is a comma 0, this is minus a comma 0. Equation of the ellipse, now you have to solve for x. So x square by a square is 1 minus y square by b square. So x is plus minus under root 1 minus y square by b square. So since we are taking this portion of the ellipse, so x will be positive under root, and the required area is 4 times area of ellipse is 4 times this area, which is y goes from 0 to b x dy. So we get 4 times 0 to b, x is a by b under root b square minus y square dy. So value of this integral is 4 a by b 1 by 2 y under root b square minus y square plus 1 by 2 b square sin inverse y by b 0 to b. So you get 0 plus at b it is 0, then at b it is 1 by 2 b square pi by 2 minus 0, then again it is 0. So you get pi ab. With these two examples of area and circles, by using both vertical and horizontal strips, you can see how to compute area of simple curves. Let us complicate the situation and let us find out area bounded between a line and a curve. So in this series, let us take example 1, the area bounded between y equals to 1 and y equals to x square. So let us plot both of them first. So y equals to 1 is a horizontal line parallel to x axis, and y equals to x square is parabola whose vertex is 0 0 and axis is y axis. So, required area is this. So, we can use horizontal strip over here. So, also you can see that this y equals to x square is symmetrical about y axis. So, the total area required is equal to twice of area shaded by green. Say, so twice of area A. So, we will be using horizontal strip. So, we get this is dy and this height of the strip is x. So, we get x dy is the area of this horizontal strip, and then total area will be, if you put the values of y from here to here. So, y goes from 0, this is 0 and it goes to 1. So, y equals to 1. Now, x is root y. So, x, the value of x is governed by the equation of the parabola, because the horizontal strip is ending at the parabola. So, height of this strip is governed by function value from parabola. So, x is therefore root y. So, you get 0 to 1 root y dy. So, 2 y to the power 3 by 2 by 3 by 2 0 to 1. So, you get 4 by 3. Now, let us do it by vertical strips. So, by using vertical strips or vertical elementary area, elementary rectangles. So, let me draw it again. This is your y axis, this is your x axis, and this is y equals to 1, this is y equals to x square. So, if you take vertical strip, what problems will occur? So, if you take vertical strip, so what will happen? By integrating y dx from here to here, or even by multiplying it by 2, you will not get the required area, because y dx, if you apply for this parabolic region, you get this area, which is not the required area. So, how to use this vertical strip to compute the area? To see that, let us draw the figure again. So, what we can do is, we can, so required area is this area minus, so required area is area shaded by red color and minus area shaded by green color. So, area shaded by red will be equal to y dx. X goes from, you have to find out this value and this value. For that you have to solve y equals to 1 and y equals to x square. That will give you x equals to plus minus 1. So, this is x equals to 1 and this is x equals to minus 1. So, area of the rectangle will be from minus 1 to 1. Y is, this y is coming from the line y equals to 1 minus y dx. X again goes from minus 1 to 1, but this y is being computed from the parabola. So, you have required area is minus 1 to 1 dx minus minus 1 to 1 x square dx. So, this is equal to 2 minus x cube by 3 minus 1 to 1. So, 2 minus 2 by 3, which is again equal to 4 by 3, same as the previous calculation. So, to compute this area of area of this rectangle, we have taken this strip and to compute this area of the region which is lying below parabola, we have taken this rectangle, vertical strips, and hence we have to subtract two areas to get the actual area, which is this, by using method of vertical strips. Let us take another example, and the example is the area bounded between y equals to x, y square equals to 2 minus x and y equals to 0, which is in first quadrant. So, let us draw it. Y equals to x is this line, and y square equals to 2 minus x is a parabola whose vertex is 2 comma 0. So, we have this kind of situation, and the required area is this, the area bounded between the line, the parabola y equals to 0, and which is lying in the first quadrant. So, to solve this integral, we need to find out, this is 2 comma 0, this is 0 0, we need to find out coordinate of these 2 points. So, we solve it and see that x is equal to so this is 1 comma 0 and this is 1 comma 1. So, the total area required is A1 plus A2 . A1 is this area, A2 is this area. So, A1 is given by y dx. X goes from 0 to 1 plus y dx, and for A2 this x limit will be from 1 to 2. This y is equal to x and this y is equal to under root 2 minus x. So, total area required is A1 plus A2. A1 is 0 to 1 x dx plus 1 to 2 under root 2 minus x dx. This is equal to 1 by 2 x square 0 to 1 plus 2 minus x 3 by 2 by 3 by 2 minus 1 to 2. So, we get 1 by 2 minus 0 plus at 2 it will be 0. So, 0 minus at 1 it will be 1. So, minus 2 by 3. So, total area is 1 by 2 plus 2 by 3. So, 7 by 6. Today we have seen how to find out area of simple curves, and we have computed area of circles, ellipse, and then we move towards little complicated cases where we have seen how to compute area of region bounded between a curve and a line. Some more problems are left in this category where area we are looking for area of region bounded between a curve and a line, and more complicated examples will be taken in further classes. Thank you.